A single railroad rail measuring roughly 330 feet in length can weigh more than 13,000 pounds. It's an extraordinarily strong steel bar, capable of withstanding immense structural stress and enduring decades of continuous use under the most demanding conditions. But have you ever wondered how iron is processed and transformed into these incredible steel bars? Today, we're visiting specialized facilities that manufacture giant rails and following real-life mobile factories to discover exactly how train rails are produced and installed on railway lines. Stay with me until the end, because what you're about to discover will change the way you look at every train that passes in front of you. Rail lines carry trains that reach the staggering speed of 217 miles per hour, roughly equivalent to a Formula One car at full throttle. But unlike a racing car that weighs around 1,800 pounds, a train carries hundreds of tons. Conventional rails simply couldn't withstand the extreme stresses imposed at those speeds. The core problem lies in the joints and sharp angles along the track. On traditional rails, every time a train passes over a joint, it generates an impact and that familiar metallic clang. At 186 miles per hour, those small impacts would become violent blows, capable of seriously damaging the track structure and triggering catastrophic accidents like derailments. To guarantee a smooth and safe journey, the solution is to eliminate joints entirely and design extremely gentle curves. That requires manufacturing continuous rails that can stretch longer than a football field. But how is a piece of steel that massive actually made? The story of these giant rails begins at specialized steel plants, and the process is a remarkable spectacle. It starts with iron ore, coke, and limestone being fed into a blast furnace, where burning coke generates temperatures exceeding 2,900 degrees Fahrenheit, completely melting the ore and separating its impurities. Liquid iron collects at the base of the furnace, while impurities form a slag that floats on the surface and is continuously removed. The liquid metal is then transferred to large ladles, where its chemical composition is fine-tuned with the addition of elements like carbon and manganese, giving the material the strength and durability it needs. This alloy travels through channels lined with refractory material that protect it from contact with oxygen. The molten steel is then directed into water-cooled molds, where it begins to solidify into continuous blocks called billets. Still glowing red-hot, these billets are cut with acetylene torches into 40-foot segments and left to cool naturally. They're then transported to a reheating furnace, where they remain for 7 hours until reaching approximately 2,300 degrees Fahrenheit, making the material pliable enough for the stages ahead. From that point on, a new glowing bar emerges every 5 minutes. Before entering the rolling mills, the hot steel is coated in a layer of oxides called scale. The moment it leaves the furnace, high-pressure water jets blast the surface. Upon contact with the extreme heat, the water vaporizes instantly, and that violent expansion blasts away any surface impurities, leaving the metal clean and ready for the next stage. With the surface prepared, the billet enters a sequence of rolling mills, enormous sets of steel rollers spinning with colossal force. With each pass, the billet is compressed and elongated, gradually thinning and taking shape. This happens across multiple successive stages, each one refining the profile with millimeter precision. What began as a solid block slowly transforms into the distinctive cross-section of a rail, a wide base, a narrow web, and a rounded head. By the end of the process, the rollers have stretched the metal to lengths of up to 400 feet. When rolling is complete, the rail is still extremely hot, but already has its final shape. This is when it receives its markings. Still glowing, it passes through systems that engrave information onto its surface: the manufacturer's name, the rail type, and production data. It's then cut to the specified length and sent along a long, controlled cooling line, where its temperature drops gradually to prevent internal stresses that could compromise its strength. Although the rail now has its final shape, the upper surface, where wheels make contact, is still relatively soft. The controlled cooling process alters the steel's microstructure, making that area significantly harder and more wear-resistant. The result is a surface capable of withstanding continuous wheel contact for decades of heavy use, providing greater stability and safety for high-speed trains. When the rail exits the cooling process, it isn't perfectly straight. To correct that, it's fed into a straightening machine equipped with 2 sets of large-diameter rollers. The first set presses the steel vertically, up and down. The second set works horizontally, side to side. The machine bends the rail beyond its natural curvature point, forcing the steel fibers to realign. It's a delicate balance. Too little pressure, and the rail springs back to its original curve. Too much, and the steel weakens. Laser sensors continuously measure any deviation and automatically adjust the roller pressure in real time. Before leaving the factory, every rail undergoes a thorough inspection, moving along the line at about 5 feet per second. A system of cameras and lasers continuously analyzes its geometry, detecting any deviation to within 1/10 of a millimeter. Magnetic testing then comes into play. By magnetizing the steel, any surface discontinuity causes variations in the magnetic field, revealing cracks invisible to the naked eye. Ultrasonic systems emit sound waves that travel through the material, identifying internal inclusions, impurities, or microfractures. If any anomaly is detected, the rail is immediately pulled aside for detailed manual inspection. Critical defects result in the piece being rejected, because the safety of thousands of passengers depends on the absolute integrity of every rail installed. The final challenge is transportation. How do you move a 400-foot, 15,000-pound steel bar? Cranes fitted with giant electromagnets lift the rails with impressive force. They're loaded onto ultra-long flat cars, separated by just a few inches, and protected by supports and shock absorbers to prevent any contact between pieces. Any damage during transit could compromise the steel and send it back to the furnace. Installation is carried out by a machine known as a track renewal train. Essentially, a rolling factory hundreds of feet long, capable of executing every step of the process in one integrated operation. These machines can lay between 1,600 and 6,500 feet of track per day, work that previously required weeks and hundreds of workers. The machine advances slowly along the rail bed, while hydraulic arms position the long rails. An internal conveyor system moves concrete sleepers into place, while rollers guide the heavy steel rails and deposit them with precision onto the base plates. As soon as a rail is positioned, automated units fasten the clips, securing the rail firmly while still allowing the flexibility needed to accommodate thermal expansion. The tamping machine then moves in. Equipped with vibrating rods, it plunges into the ballast and packs the stones tightly under the sleepers, creating a stable, perfectly leveled base with the exact cant required, especially on curves. For high-speed trains to travel at over 186 miles per hour in complete safety, and without the characteristic noise of joints, the rails are welded together into a single continuous structure, stretching for miles. A ceramic mold is placed around the junction of two rails, leaving a small gap between them. In a crucible positioned above the mold, a mixture of aluminum powder and iron oxide is ignited, triggering a chemical reaction that reaches approximately 4,500 degrees Fahrenheit within seconds. The liquid steel flows into the mold, filling the gap and fusing the ends of both rails into one seamless structure. After cooling, the mold is broken away, and a grinding machine smooths the surface until the joint becomes almost imperceptible to the touch. And that's how rails are manufactured, installed, and welded, forming continuous lines capable of supporting the weight and extreme speeds of modern trains with smoothness and total safety. Thank you for watching. If you have suggestions for our next video, share them in the comments below.